Hi everyone, in this video we're going to be going through section 7.2, applications of the standard normal distribution. So we were introduced to the normal distribution, talked about its properties in the previous section. Now in this section we get greater detail about how we find the area under the normal curve. And it all starts with the z-score. So remember that z-score formula, z equals x minus mu over sigma. That is coming back and will be present throughout the rest of the semester, throughout the rest of the course. So we start out with the next part. Suppose a random variable x is normally distributed with a mean and standard deviation. Then that z-score is that z is normally distributed with a mean of 0 and a standard deviation of 1. Okay, so what that means is that if I have any data set with a mean, any mean and any standard deviation, in computing the z-score, z equals x minus mu over sigma, we get a normally distributed variable that has a mean of 0 and a standard deviation of 1. So when you compute the z-scores, remember we talked about how you can compare different data sets to each other. That's because you are standardizing, normalizing that distribution. And so that this is what our z distribution, see the z over there in the corner, the z distribution looks like. Mean is 0, standard deviation is 1. And the purpose for that, why that is necessary and helpful, is so that we can we can develop basically a table that we'll use to look up and find exact areas under specific under all these values, under specific values under that curve. Okay, now I apologize for the terrible color quality on this next slide here, but I had to take a photo with my tablet of my textbook, so it just looks pretty bad. It looks like an amateur did it and who's just trying to do the best he's got. But here's what we're looking at. So this is in a table in the fold-out section in the back of your book if you have a hard copy of the book. If you use MyMathLab, then you can also access this table through MyMathLab. It is table number, where's my highlighter? Table number 5. Yellow doesn't show up. Let's go blue. Table number 5. There it is right there. And it is the standard normal distribution table right there. Okay? All right, and there's a ton of numbers when you look at it. But what I want to first focus on is up here. All right, what it gives you, this table gives you, is the area underneath our normal curve, our bell curve, to the left, right, to the left of some z-score. Okay, so if I find a z-score, and let's say my z-score is negative 1.52. Okay, I compute a z-score. It's negative 1.52. What I do first is I not scroll, but I look down the left-hand side of the table until I get down to negative 1.5, which is right here. And then I go over to the right, and if you look at the top of the table, there's 0.00, 0.01, 0.02. So that gives you accuracy to the nearest hundredths place. So I'm going to go back down to negative 1.50, 1.51, 1.52 right there, and it's 0.0643. All right, so what that means is that a z-score of negative 1.52 corresponds to an area of decimal point 0.0643. And let me just verify that. It was this one. Yep. And so if my z-score is this z-score right here, negative 1.52, then the area of this stuff here is about 6.5%-ish. 0.06 is about 6%, excuse me. So that's what that area represents. 6% of the stuff under the curve, of the area under the curve. Okay? We'll just do one or two more here. Let's say I have a z-score of decimal point 0.03. Okay, 0.03. So where am I going to go on my distribution? I'm going to keep scrolling down. And oh, by the way, in MyMathLab, they break it up into 2 pages. There's 2 pages. All right. There's the first page is like the negative side of the z table with all the negative z scores, all these guys. That looks terrible. And then the second page is the positive side of the z table. So as I scroll down here, you can see there's even more numbers if you use the book. But if you use MyMathLab, it breaks it up into 2 pieces. All right, so let's go z equals 0.03. Now notice it's positive, so I'm down here at positive 0.00. And what you notice at 0.00 is 50%, because a z-score of 0 has half the distribution to the left, half the distribution to the right. Okay, so that's 0, 0, 0, 1, 0, 2, 0, 3, 0.512. The area is decimal point 5120, or about 51%. All right, and then, hey, why don't we do one more? Let's say that I have a z-score of 1.38. 1.38. So I'm going to go down a little bit lower here. There we go. 1.3 is right here, and then 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. 0.9162. So the area there is decimal point 9162. Okay, so that's how you use the Z table. In our first example, we go back to that the previous section where we talked about the 200 little 3-year-old females and at a pediatrician, and we're given the mean of those little kids. So mu is equal to 38.72, and the standard deviation sigma is 3.17. All right, it says use the normal model to determine the proportion, the percent of 3-year-old females that have a height less than 35 inches. So in this problem, the x that we're talking about is 35 inches. So I've got the two steps kind of over here. First, we're going to find a z-score. Z equals x minus mu over sigma, and I have all that written down. And then we're going to go to the table and look up our area and then write a sentence as a proportion. Okay, so my x in this problem is 35 inches. Mu, the mean, 38.72 over sigma, 3.17. Punch that into my calculator, and I get a z-score of negative 1.169, so we'll round that to 1.17. For these z-scores, we're always going to use 2 decimal places because that's as accurate as Table 5 gets. It wants the z-score to 2 decimal places. Okay, so now I go over to my table the same way we did on the last slide and find the area that negative 1.17 corresponds to, and find that it is an area of decimal point 1210. Okay, so that is the math, the work involved. And then what we're going to do is write a sentence like answering this question, because we want the proportion of 3-year-old females that have a height less than 35 inches. And so what we'll do is we'll say that 12%, or I mean, I'm just rounding to the nearest whole percent, of 3-year-old females have a height less than 35 inches. And that's the end of that question. In the next question, we're looking at the probability that a randomly selected 3-year-old is between 35 and 40 inches tall. Okay, so what we did in the last example was for 35 inches, we got a z-score of negative 1.17 and an area of 0.1210. So that's just going to save us a little bit of work. All right, and what we need to do with this one, and I'm going to draw the normal distribution for this example to kind of show you something. So I am going to draw my bell curve there. That looks pretty decent. And let's see, if our mean is 38, so 35 is a little bit less, 40 is a little bit more, we already know that from 35 inches, to the left of that is about 12% of the distribution. That's what we already did in the last example. Well, if I compute a z-score for 40 inches, which is a little bit more than the mean, maybe 40's over here. Try that again. Maybe 40 inches is over there, approximately, right? If I look up a z-score and a corresponding area for 40 inches, I'll get everything to the left of that. Well, if I just want what's between 35 and 40, if I just want this part, well, I get that by subtracting the 2 areas, the 2 percentages that I look up on the table. So compute 2 z-scores, look up 2 areas, then subtract them. Those are kind of the steps that we're looking at here. All right, so the next step, so I have my z-score and my area for 35 inches. Now we'll do the same thing for 40 inches. 40 minus 38.72 divided by 3.17, x minus mu over sigma. Punch that into your calculator, and you get 0.403, but I'm just going to go to two decimal places, 0.40. Now, when you go to Table 5, look up that z-score, you will find an area of 0.6554. Okay, so we have the area to the left of that z-score. We have the area to the left of that z-score. To get the area that's between the two z-scores, we're going to take 0.6554 and subtract 0.1210, and we'll get an answer of 0.5344. Okay, so that is our answer. But then can we write down some sentence that shows that we know what that means using the context of the problem, probability? There is a 53% chance that a randomly selected 3-year-old female is between 35 and 40 inches. If you look at the percentages on this slide, these should kind of look familiar. This is just kind of here to point out that what we talked about earlier in the semester with the empirical rule, that 68, 95, 99.7 rule, that comes from the work that we're doing now. That's just a more simplified version. It's a quicker, just to know what's happening at the 1 and the 2 and the 3 standard deviations away from the mean. But the work that we're doing in this section is that, but in way greater detail using this giant, massive table of numbers. Okay, but all of those percentages that we worked with previously are rounded values of this normal distribution. In this next example, we do things a little bit differently. Notice the difference in the wording, where they're asking what is the height of a 3-year-old at the 20th percentile. Okay, so what that means is I'm just going to draw a little normal distribution here. There we go. What that means is if I'm in this problem, I'm given the 20th percentile, so that means that 20% of the stuff of the 3-year-old's heights are to the left of some unknown z-score. So I don't have the height, I have the percentile. So I get the stuff, let me use a different color, I get the stuff under the curve, 0.20. So when we're given the percentile in this case, what we have to do is look a little bit differently, treat it a little bit differently. So I'm going to start out with, I need to find the 20th percentile in the table. So that's what we got to do. We kind of scroll back and forth. Actually, what I've found works best is if you start in the middle, I usually use 0.04, start in the middle and look down until you get close to 20%. And it's going to be down here towards the bottom here, right? So here I've got 7%, here I'm at 9%, 10%, 12, 14, 17, 20. Oh, there it is. And then you look left and right and get as close to 20% as you can. See here I'm getting further away. So this one was pretty good. And here I'm below and getting further away from 20%. So I'm going to go back to this number. Hey, I started in the middle, and that was actually the right number. Okay, so now I've got to look to the left and look up to know what my z-score is. So from here to the left is negative 0.8, and up is 0.4. So that corresponds to a z-score, so the 20th percentile corresponds to a z-score of negative 0.84. Okay, so this one a little bit different. We got to start on the inside and go to the outside of the table. All right, so what do we do with that? That's not the answer to the question. That's just the z-score. So now, how tall is that little 3-year-old? So we're going to say, all right, my z-score formula is x minus mu over sigma. I just found that the z-score is negative 0.84, and then the x is what I'm looking for, mu 38.72 over sigma 3.17. And hey, look at this. We got to solve for x. We're doing a little bit of algebra here, so move that up. To solve this equation for x, we have 2 steps. The 3.17 is in the denominator. We're going to multiply both sides by that denominator, 3.17. And so when I multiply negative 0.84 by 3.17, I get negative 2.6628 on the left-hand side. The 3.17s cancel each other out, and we have x minus 38.72 on the right-hand side. Continue solving this equation for x. Add that 38.72. And we're going to find that x equals, plus 38.72, x equals 36.0572. And we'll round that approximately equal to 36 inches. Okay, so then to go back to the beginning of the problem, what does that 36 inches represent? That is the height of a 3-year-old in the 20th percentile. They're taller than 20% of the population and shorter than the rest. All right, here's our last example for the section. We're taking the SATs, just looking at the math portion of the SATs, and the scores are approximately normally distributed, so we can answer this question using Table 5, with a mean of 516, standard deviation of 116. Then the question asks, what's the probability that a student scores better than, we haven't encountered that, it's always been less than, but better than 750? Well, to start out answering the question, we need to find a z-score. So we're going to take and substitute into our z-score formula. X is 750 minus the mean is 516 divided by the standard deviation, 116. Type that into your calculator, 2.01. I should have said this earlier, just a note about the calculators. If you're typing this all in one step, you need an extra set of parentheses around that numerator. But my suggestion would just be to do the subtraction, hit enter, and then do the division. Okay, so just something to keep in mind. If you're doing it in one step, you need parentheses. 2 steps, you don't. Okay, so I got a z-score of 2.01. And what I want to do is I'm going to start out, I'm just going to draw my distribution first. Draw my normal curve here. There it is. Looks pretty terrible. These are hard to draw on a tablet. I'm much better drawing them on a chalkboard. And 750, that's pretty good. 516 is in the middle here. 516, that's the mean. 750, somewhere over here to the right. Okay, so there's 516. 750, and I want the probability that they do better than. I want the stuff to the right of that score. Okay, well, what we do is we still use Table 5 and get everything to the left, and the only difference is we're going to subtract that amount from 100% minus everything to the left gives me everything to the right of that score. Okay, so we've got our z-score of 2.01. I'm going to go over to Table 5 and find that 2.01 corresponds to an area of 0.9778. And then that's the area to the left. Area to the left. And the area to the right of that z-score, we're going to take 1 minus 0.9778. So that is 1 minus 0.9778. And we get 0.0222, 3 twos, or about 2%. So there's about a 2% chance that a student scores better than 750 on the SATs. Okay? Cool. All right, what we can do also is write our notation a little bit more formally. I won't do this super often, but I like to at least show it that there is a way to more formalize this notation, right? And because this is a probability question, and normally with a probability question we write p parentheses. What is the probability that x is greater than 750? What's the probability that they score better than 750 on the SATs? Well, that is equal to the probability that their z-score is greater than 2.01. All right, that's like equivalent to finding the z-score step. And then that's equal to 1 minus the probability that z is less than 2.01. And then that probability that z is less than 2.01 is the 0.9778. Okay, so that's like the more formal notation. I'll sometimes use it. I sometimes won't. But that way, you've heard it at least for when you see it again. Okay, and there was a second part to this problem. This video is kind of long, so I think I'm going to skip the actual solving of it. But it asks what scores separate the middle 90% from the top and bottom 5%. And what you do with that one, let me go green here. I'll just add it onto my curve, right? There's 5% at the bottom, 5% at the top, right? 0.05. 0.05, and this is one where you have to start on the inside of the table and you find the z-score that corresponds to 5%, and then you find the z-score that corresponds to 95%, and then you work backwards. You solve for the x value. So you go in the middle of the table, find two separate z-scores, and do a couple of algebra equations to solve. Okay. If anyone has questions about that one, or if it comes up in a homework, let me know, and maybe I'll post a follow-up video explaining how to do something like that. But thank you for listening. Get to work on this homework.